be going through some dirt on your spring assessment that you've just completed. So in this video I'm going to go through our energy profile explanations. The key point here is really what the question is asking us, how it's asking us to define exo and endothermic reactions. So here it was asking us to define it in terms of bond energy, in terms of bonds being broken and bonds being made. But a lot of our answers were defining it in terms of it being energy released to the surroundings for an exothermic reaction. But actually that wasn't giving the answer that the question was after. So like, whilst that's still a correct definition of exothermic, it wasn't what that question was after. We're also going to look at crude oil separation, just making sure that we're aware of all the points that we needed to have included to get those 4 marks. I will then do a workthrough of those 2 calculation questions, so the limiting reagent and our mass and moles of oxygen. Okay, so we're going to start off by looking at our reaction profiles. So I've got 2 diagrams here, one for my exothermic reaction and one for my endothermic reaction. First thing I want to do is just remind us that our reactants start off on the left hand side, and then we've got our products on our right hand side, as this is the direction of our reaction pathway. Another thing just to label is that this bit here is our activation energy, and so this is our energy required for the reaction to happen. So it's minimum energy. Another thing that we can look at is our overall energy change. So from where our reactants are to our products, we've gone down, so this is a negative change. Whereas here, where our reactants are to our products, this has been a positive change. So as this is a negative change, it means that energy has been released to the surroundings, and therefore our temperature of our reaction mixture would increase, whereas here we've got a positive change, so our energy has been taken in from the surroundings, and as it's been taken in, that's going to mean that our temperature of our reaction mixture is going to have decreased. But we also need to think about what's happening in terms of our reaction. So if I'm starting off with some reactants and I then make my products, in order to get there I've had to break my bonds between my blue circles, and I've had to break my bonds between my pink circles, and then I've had to make bonds between my blue and my pink circles. So going up, we have broken bonds, and going down we have made bonds. And this is the same whether it's exothermic or endothermic. So going up we break bonds, and going down we are making bonds. Now if you look at the size of my arrows, granted they're curved so it's not exact, but here we can quite clearly see that going down, that making bonds, is greater than breaking bonds. Whereas here our breaking bonds is greater than making bonds. Just a note on our terminology, when we make bonds, as you can see this is a negative change, so this must mean that energy is released. As it's an exothermic process, whereas when we break bonds this is a positive change, and so we are taking in energy, we're absorbing energy. And so in terms of why a reaction would be exothermic, well, it's that our energy that's been released when we've made bonds is greater than the energy that was absorbed when we break bonds. So exothermic, energy released when making bonds was greater than the energy absorbed when breaking bonds. So this is our definition in terms of making and breaking bonds. This is our definition in terms of energy released from the surroundings, but we could also define it in terms of their relative positions, that are it's exothermic when our products is lower in energy than our reactants. So this is our definition in terms of our energy of our reactants and our products. And similarly we do the same thing for our endothermic. So it's endothermic when the energy required to break bonds is greater than the energy released when making bonds. So, key thing to remember here is that our breaking bonds requires energy in order to do so, whereas our making bonds, you release energy in doing that. So you've got to be really careful that we say it in the right way. A lot of us were saying that making bonds requires energy, but it doesn't, it releases energy. Just our final thing with endothermic, our products are higher in energy than our reactants. So that's the definition comparing our energies of our products and reactants. So 3 different definitions of the same thing, so we have to be careful in terms of what the question is asking us, how it's asking us to define it. It might even say how would you know in a reaction that it was exothermic? And you'd know because your temperature would increase. If it was endothermic, your temperature would decrease. Moving on to our fractional distillation, separation of crude oil question. I quite like this diagram because it's got our different temperatures and it's got the different fraction names as well as images of their uses. So the key thing to start us off with is this bit at the bottom here. So here our crude oil is passed into a furnace. This furnace vaporizes our crude oil. And is then passed into our fractionating column. And what you can see here is that this fractionating column has a temperature gradient, and it's very clearly shown here in colour, going from 25 degrees Celsius to 350 degrees Celsius. This colour scale is also really nice in showing us the actual different colour scale of the fractions themselves. Our colour is much lighter for our short chain hydrocarbons, whereas it's much darker for those long chain hydrocarbons. So our second bit is the vapours are passed into a fractionating column. Which has a temperature gradient, which just means it's hotter at the bottom and cooler at the top. So then the third thing we can say is that our vapours rise through the column, as they are gases, so they're going to rise. As they rise at their boiling point, they're going to cool and condense. When the hydrocarbon reaches its boiling point, it will cool and condense to be collected as a fraction. And simply saying our fractions are separated due to different ranges of boiling points. Now notice I didn't say different boiling points, because remember our fractions are still a mixture. There are a variety of hydrocarbons that make up diesel or fuel oil, or gasoline, which of course is our petrol. So it is a mixture of hydrocarbons. Each hydrocarbon has a specific boiling point by which it's separated, and so our fractions, they have a temperature range. So here 220 to 250 degrees Celsius. but when that gets tapped off, that's diesel. Paraffin has a different temperature range for the hydrocarbons that are tapped off there. It's not a specific hydrocarbon. Specific hydrocarbons have a specific boiling point, but our fractions have a range of boiling points, as they are still a mixture. Okay, so this next question is our limiting reagent question from the assessment. Please also note it says you must include calculations in your answer. So if you got the correct limiting reagent but you didn't show your workings, we can give you the full marks as you hadn't shown your calculations. Equally, some of you had done part of the calculation, but there was a crucial step, which I'll highlight when I do it, that you needed to have included to show that it was the limiting reagent. So first things first is working out our moles of butane. So remember, moles equals mass divided by mR. We've got our mass of 14.5 grams from our question, and we can work out our mR of butane, which is C4H10. So we're going to have 4 lots of 12, as that's our atomic mass of carbon, plus 10 lots of 1, as that's our atomic mass of hydrogen. That comes out to 58. So our moles of butane we can get by doing 14.5 divided by 58, which comes out to be 0.25 moles. So then, looking at our question, 2 to 13 ratio, so our 0.25 is worth 2 parts, so 13 parts is going to be 0.25 divided by 2 to get 1 part, and then times by 13. So that comes out to be 1.625. So now we need to find out how much oxygen we have to then establish which our limiting reagent is. So our moles of oxygen is our mass divided by our mR. Mass we've got from the question, 72.0 grams. And then our mR, remembering oxygen is diatomic, so 2 lots of 16, 16 being the atomic mass of oxygen, but remember it's O2. So then our moles of oxygen is 72.0 divided by 32, and this comes out at 2.25 moles. So then this is our crucial step here. So 2.25 is greater than that 1.625 that we needed of the oxygen in order to react with all that butane. So as the amount of oxygen we have is greater than the amount of oxygen we needed for this amount of butane, our oxygen is in excess, and therefore butane is our limiting reagent. So we must have calculated the 1.625 and compared it to the 2.25 in order to get our full 4 marks. Finally, just our question on our mass and then our moles of oxygen. So here we've got 6.8 grams of hydrogen peroxide decomposing to form 3.6 grams of water, and we're asked what our mass of oxygen is. Now, lots of us did this through moles and mR calculations, which is absolutely fine, it will get you the same answer. However, there's an even simpler way of doing this. If we remember our law of conservation of mass. That tells us that mass cannot be created or destroyed. Therefore, our mass of our reactants is equal to our mass of our products. So 6.8 grams is equal to 3.6 grams plus our unknown mass of oxygen. And then it just becomes a simple subtraction. 6.8 minus 3.6 gives us 3.2 grams of oxygen. How many moles of oxygen is that? So if you got the wrong answer in this question, you still got your answer, you still got the marks for the second part, provided you got the right MR of oxygen. Oxygen molecules, it's O2, so our MR is twice the relative atomic mass of oxygen, so 2 times 16, which is 32. So then we're doing 3.2 divided by 32, as that's our mass divided by our MR to give us our moles. 3.2 divided by 32 is 0.1 moles. You still get the mark so long as you have divided by 32.